In this video, we're going to find x and y such that x equals 3x squared y minus y cubed and y equals x cubed minus 3xy squared. Before we move on, don't forget to give a like, subscribe to my channel, and turn on post notifications. The first method that came to my mind was to multiply the first equation by y and the second equation by x so that xy is on one hand equal to 3x squared y squared minus y to the power 4, that's from the first equation, while on the other hand is equal to x to the power 4 minus 3x squared y squared. Then you can equate these two expressions, and so therefore we have x to the power 4 minus 6x squared y squared plus y to the power 4 equals 0. And you can solve for the ratio of x and y by looking at this quartic equation. And by solving that using the quadratic formula, you have x over y all squared equal to 3 plus or minus 2 times square root of 2, and if you take square root, it is actually root 2 plus 1 or root 2 minus 1. So this ratio x over y can be either plus or minus root 2 plus 1 or plus or minus root 2 minus 1. So there are many of them, and there are many cases to settle. So this is not my ideal approach to this problem. In fact, I noticed that the terms at the right of the two equations, say x cubed, 3xy squared, 3x squared y, and y cubed, are actually part of an expansion of x plus y all cubed. But there are some slight difference between x plus y all cubed and the arrangement of these four terms. The reason is that the signs are a bit different. There are minuses within the two equations. So maybe we can try to connect these two equations with x minus y all cubed instead, because then this expansion will be x cubed minus 3x squared y plus 3xy squared minus y cubed. So at least we have a minus y cubed at the end and the same term in the first equation. But it still wouldn't work because the signs of the two middle terms over here are swapped. So we have to find another way out, but we're actually really close. In fact, we can take a look at x plus iy all cubed. In other words, we are considering complex numbers. So for x plus iy all cubed, for x and y being real numbers, is equal to x cubed plus 3x squared times I times y plus 3x times I times y all squared plus I times y all cubed. And if you simplify, you will have x cubed minus 3xy squared, that's the real part. As for the imaginary part, we have I times 3x squared y minus y cubed, because I cubed is minus I. So now from this, we've finally obtained a similar structure as the right side of the two equations. We have x cubed minus 3xy squared equal to the real part, while 3x squared y minus y cubed is equal to the imaginary part of x plus iy all cubed. If you put this together with our two equations, then we can say that therefore we have x plus iy all cubed is equal to y plus ix And if we take out I on both terms at the right, we have I times x minus iy. And so letting a complex number z equals x plus iy, where x and y are real numbers, then we can say that z cubed equals I times z conjugate. The conjugate of x plus iy is defined by x minus iy. Now from this, there are two cases to settle. To decide which two cases are we considering, I'm going to consider the modulus of both sides. Which means the length of the segment or the distance from the point between the point and the origin when this complex number is plotted on the Argand diagram. Geometrically speaking, for a complex number, if it's plotted in this way, z equals x plus iy, then the conjugate is defined by the reflection of that point with respect to the real axis. And so that means they should have the same modulus. The modulus of z cubed should be equal to the modulus of I times z conjugate. Then the modulus of z cubed is equal to the cube of the modulus of z, and that equal to I is just 1, so 1 times the modulus of z. So now we can solve a real cubic equation. And this modulus is either 0, 1, or minus 1. But of course, it can't be minus 1 because it's about a distance. If the distance is 0, then it's just overlapping with the point, but it just can't be negative. So the two cases are either the modulus is 0, that means z equals 0, which means x and y are both 0. And otherwise, for the case that the modulus of z is equal to 1, then we know that the so-called x and y, we have x squared plus I squared, x plus y squared equals 1. And because whenever a complex number is multiplied by its conjugate, it's actually real, noticing that there's a plus and minus over here, the difference of squares identity will give the product to be just the sum of squares of the two parts. And so that means it's equal to the square of the modulus, and that's 1. So therefore, going back to the equation that z cubed equals I times the conjugate of z, we can say that z cubed is equal to I times 1 over z. And so this equation is purely on the complex number z. And now we have z to the power 4 equals I. For the last step, to find out our solutions to this problem, we need to consider the polar form of a complex number. Noting that this complex number z has modulus 1, I'll just let z be e to the power I theta, where theta is defined by formally speaking, we'll say that as tangent theta equals the imaginary part over the real part, but if we go back to the arcane diagram, it will be this angle. The angle that is formed by rotating, starting from the positive real axis in the anti-clockwise direction to the segment that joins the complex number and the origin. So using this definition, I'm going to rewrite I as its polar form as well, and in fact is equal to e to power I times pi over 2. Whereas for z to power 4, it's going to be equal to e to power I times 4 theta. And so 4 theta has to be equal to pi over 2 plus multiple of 2 pi. Or I'll write that as 4 theta equals pi over 2 plus 2k times pi, where k is an integer. So then by solving, we have theta equals pi over 8 plus a multiple of pi over 2. And this means that by looking at the polar form of z, which can also be written as cos theta plus I times sine theta, then we will have x equals cos theta which is pi over 8 plus a multiple of pi over 2, and at the same time y has to be sine of pi over 8 plus the same multiple of pi over 2. Under the structure of the solution, there are actually only 4 choices of k, which are just 0, 1, 2, and 3, because starting from k equals 4, that is 4 times pi over 2 is 2 pi, and by the periodicity of cosine and sine, the values will just repeat itself. So I can say that x and y can either be cos pi over 8 sine pi over 8, or cos 5 pi over 8 sine 5 pi over 8, cos 9 pi over 8 sine 9 pi over 8, and finally cos 13 pi over 8 and sine 13 pi over 8. Please feel free to share your ideas in the comments. Thank you for watching. See you next time.